Next up, I'm excited to introduce Nadia Fawaz. Nadia is a senior staff applied research scientist and the tech lead for inclusive AI at Pinterest. Her research and engineering interests include machine learning for personalization, AI fairness, and data privacy. And her work aims at bridging theory and practices. She was named one of the 100 brilliant women in AI ethics 2021. Her work on hair pattern search was recognized in the AI and data category on Fast Company's 2022 World-Changing Ideas list. Earlier, she was a staff software engineer in machine learning at LinkedIn, a principal research scientist at Technicolor Research Lab, and a postdoctoral research at MIT Research Laboratory of Electronics. She received her PhD in 2008 and her Master of Science in 2005, both in EECS from Technicom Paris Tech and Eurocom France. Nadia, over to you.
Hello, I'm Nadia Fawaz, an applied research scientist and the technical lead for inclusive AI at Pinterest, and I will be presenting today how we build inclusive search and recommendations. This work is the result of a cross-functional collaboration with many talented peers at Pinterest, as developing inclusive AI in the product requires a multidisciplinary approach, not just technical skills. So I would like to start by sharing some feedback a pinner sent us a few years ago. She told us that to see people of color in our app, she needed to physically type the word black, and that when she looked at our app, it told her that people who looked like her were not the norm. Pinterest's vision is to bring everyone the inspiration to create a life they love, and to truly be a place where everyone can find the most inspiring and relevant content for them. Pinterest is committed to content diversity and to building an inclusive experience on the platform. Machine learning powers many advanced search and recommendation systems at Pinterest. And these systems tend to be very complex, and they have many components as they need to operate at the very large scale of over 400 million monthly global active users who have saved over 300 billion pins to more than 8 billion boards in over 35 languages. And we strive to be a place filled with positivity for pinners. Now, how do these systems work? In a nutshell, this system consists of several machine learning models trained to optimize some objectives. For example, to predict the likelihood that a pin would be relevant to a pinner given a variety of inputs. They take as input the queries, and at Pinterest, our data is multimodal, so queries can be in the form of text, such as the queries typed by the user. They can be visual, when a user inputs an image to search, or they can be an entire pin. And a pin is more than one or multiple images or video. It has a title, a description, a creator, a link to a website. They also take as input user features, such as the interests that a pinner follow, and content features, such as the image, the video, and the description. And finally, they take as input past interactions with pins and boards that have happened on the platform. Pins are retrieved from our very large corpus. They are ranked and blended according to these predicted scores. And then the list is surfaced to the users in the app. Now, if the data we input in this system is not diverse, the machine learning models may learn implicit biases, serve biased results in production, leading to the collection of more biased data, and that's the creation of a bias feedback loop. We would like to move toward a virtuous circle, where we start with diverse data, we mitigate potential biases in the system, and we make the user experience more inclusive. So the goal of the inclusive AI team is to make our AI systems perform outstandingly well across our diverse sets of users, including pinners, as well as content providers such as creators and merchants, for a wide range of use cases. And developing inclusive AI requires an end-to-end iterative and collaborative development approach. We have learned the importance of building inclusive systems by design, of measuring to make progress, and of leveraging both artificial and human intelligence. And we recognize that these challenges are multidisciplinary, not just technical, so we work within a large cross-functional team where engineers collaborate with people across the organization. The word bias encompasses many complex issues, but with a simple example, I'd like to give you a little bit of intuition on what algorithmic fairness focuses on. So imagine there are two groups, one large and one small. In group A, most people prefer apples, and in group B, most people prefer pears. And we have this imaginary algorithm that looks at past data, learns that red apples are the most popular fruit, and so it starts always recommending red apples. So what is the algorithm performance? The overall accuracy is 74%, which seems to be okay. But is it fair? Now, if we take a closer look at how it performs for each group, we see that there is a gap. Errors disproportionately affect the smaller group B. And so mitigating disparities in performance between groups is the main focus of algorithmic group fairness. Now, why is it important to reduce bias? Mitigating biases allow us to move away from historical patterns of bias in society that are unacceptable today. And poorly designed systems in risky applications can lead to harm. It also allows us to work ahead of regulation. Recently, both the European Union and the US Federal Trade Commission have started issuing guidance and drafts for AI regulation, including AI fairness. Another reason why reducing bias is important is to put users first. Users care about the quality of recommendations, and improving user representation and experience can lead to more engagement, improve exposure for content providers, help grow in new markets, and retain our competitive advantage as a positive corner of the internet. And last but not least, there are technical reasons to reduce bias. It's part of good technical craftsmanship. A system that significantly underperforms on a segment of the data is not a high-performing system, and we would be leaving technical value on the table. Now, AI fairness is a nascent area. We recently saw a sharp growth in research papers, but the number of companies who build change into their technology and product is still small. And so the work we're doing at Pinterest in our products not only improves our user experience, but it also helps raise public awareness about algorithmic bias. And it can impact how the tech industry develops technology and products. So a top request we hear from pinners is that they want to feel represented in the product. This is why we build the skin tone ranges and hair pattern search. These inclusive features give control to pinners on their experience in search and AR try-on similar looks recommendation module by allowing them to narrow beauty and hair results by a skin tone range or hair pattern of their choice. So how did we build the skin tone ranges? I would like to walk you through this journey. In the early days, to understand the skin tone range in a beauty image, we considered a third-party closed-box computer vision library. It was composed of several modules. It had a deep learning module for face detection, followed by a color extraction module. We got the LAB color coordinates, threshold on the lightness, L, and used that score to estimate the skin tone range. Now, this was launched in production back in 2018, and we heard positive feedback from our users who saw their experience improve. In particular, it became easier for them to find relevant content in the darker skin tone ranges. However, over time, we started noticing issues with the performance of the closed box version based on visual inspection. But in order to make progress, we needed to quantify the extent of the issue. So we collected a diverse data set, and we worked with a specialist to label the data, and we conducted an evaluation of the closed box version using this diverse data. We analyzed the error patterns and quantified the disparities in performance across different skin tone ranges. So the confusion matrix here reveals a major coverage issue for the closed box predictions in the darker range. And we also noticed performance disparities in the granular precision, recall, and F1 score per skin tone range. So in an image, at the top, you have the ground truth diverse data set labeled by the specialist. And the middle row shows how the closed box understands the skin tone range for these images. So you can notice the coverage issue for images in the darker ranges, where the closed box cannot output any prediction, and it fails to understand the skin tone ranges accurately for many images. Now, to understand why this was happening, we conducted an error analysis of the components of the system. The top right corner shows the score distributions for each skin tone range. These score distributions are not really separable, they overlap. And the thresholds are also out of phase with the diverse data. This issue can be amplified by shadows and challenging lighting conditions. Then when we looked at the output of the face detection module, we realized that the coverage issue for darker skin tone ranges was coming from there, because the face detection module was failing to detect faces for the darker range images at much higher rates than for the lighter skin tone images. And that type of bias in face detection technology has been studied and documented by Joy Buolamwini and Timnit Gebru in the gender shades study a few years ago. So we reached the conclusion that there was no amount of post-processing on the output of the closed box system that would fix these built-in biases in its components on which we did not have control. So we needed to build our own system end-to-end, and this is what we did. In our first in-house version, we developed a system with several computer vision components. After exposure correction, it detected the location of a face, extracted facial landmarks such as the eyes, the nose, the mouth, segmented them out to output a skin mask. And in the case where a face was not detected, the hue saturation value processing module allowed to detect patches of skin pixels in the image. The skin mask was then fed into a color extraction module. We generated the LAB color coordinates. We computed the individual topology angle, and we passed that into the fairness-aware tuning phase that took as input a diverse dataset to finally output the skin tone range of the image. When we evaluated the performance of the in-house version on the diverse data, it looked much better. The confusion matrix was closer to a diagonal and more symmetric. The score distributions were more separable. And the per class precision, recall, and F1 score were not only higher for every class, but also the disparities between the classes had reduced, meaning that we had reduced bias in performance. Back to this image, you've already seen the top and the middle portions of the image. The bottom row shows the performance of the in-house visual skin tone. You can notice that we didn't have any more the coverage issues on the darker skin tone ranges. And while it was not perfect, we had made a lot of progress. Now, this was not the end. Even the visual skin tone V1 could make errors. And we learned from these errors and made the models also learn from the errors. So I would like to share some example of images that tripped the visual skin tone V1. Extreme lighting conditions are challenging. Occlusions such as beards and sunglasses could also lead to errors. And then the pandemic happened. And as the world changed, so did images on Pinterest. The pandemic caused a surge in face mask images to which the model had to adapt. In some images, there are multiple faces or a combination of faces. In other images, the face is not visible, or there is no face at all because we have other body parts. And so these cases prompted us to search for a more robust approach. So we first invested in collecting our largest and most diverse data set yet for skin tone. It included images from previous errors, partial faces and body parts to handle new cases such as nails and lips, verticals such as beauty and fashion, and internationalization. And for the system to handle more complex images, we decided to move away from face detection entirely, and we experimented with different architectures. We first used an approach that learns the skin tone range directly from the raw image pixels, using convolutional neural networks. So this ResNet model outperformed our visual skin tone V1 when evaluated on this larger, more challenging data. Then we leveraged the multitask visual embedding model that the computer vision team at Pinterest developed. This unified visual embedding powers important visual search applications at Pinterest, such as visual shopping and Lens. We added a skin tone classification task and used that to predict the skin tone ranges. And when we evaluated this approach on the more challenging data and some of the error cases I presented earlier, it outperformed face detection by a large margin across all metrics, while performing similarly across genders. And so the improved skin tone model gave us the confidence to expand beyond beauty to the fashion use case and to make skin tone ranges more prominent in the product. Now, we built on our learnings on developing skin tone ranges with bias mitigation to develop hair pattern search. Hair pattern search is also powered by a computer vision model trained on diverse data to understand the hair pattern visible in an image. To define the hair pattern categories, we consulted hair experts who work with Black, Indigenous, and people of color, including Naima Lafont, a Pinterest creator and the global artistic director of Amica, a hair brand. Their guidance, the help of our beauty and fashion specialists, along with our user research team, informed our technical choices throughout development. User research played a crucial role end-to-end in building hair pattern search, with inclusion at the heart of technical choices, from ideation to design and development to the evaluation of the production feature. To mitigate bias and ensure a consistent performance of the machine learning models across different segments of Pinterest content, we collected a diverse set of hair images across hair patterns, skin tones, genders, and hair-related interests. We integrated hair pattern prediction into Pinterest's latest visual embedding multitask model that leverages state-of-the-art vision transformers and our investments in our computer vision infrastructure to scale to billions of images. We iterated multiple times, incorporating feedback, augmenting the data, and retraining the model to make it learn from its errors. Now, today, the skin tone ranges power a more inclusive experience in 19 countries, and we launched hair pattern search in 15 countries. We worked with our internationalization team in local markets to evaluate and launch these inclusive experiences internationally. Our work on skin tone ranges and hair pattern search received global press coverage, and hair pattern search was recognized in the AI and data category on Fast Company's 2022 World Changing Ideas list with an honorable mention. So I would like to share a few learnings from going on this journey of developing the skin tone ranges and hair pattern search. So I would like to encourage you to start with diverse data, but also to remember that bias can come not only from the data, but also from the modeling choices and the evaluation processes that we choose to use during development. It's important to test and test again the performance at every step of the development, including every component within the system and every stage as we build our model, during offline evaluation, during A/B test experiments, and to continue monitoring after it is running in production. Quantifying biases and analyzing the errors at the granular level will help to iterate fast, and it's important to go beyond just the overall accuracy as an evaluation metric. It is important to also learn from the errors and to make the machine learning models learn from those errors too. Building iteratively allowed us to uncover the complexity layers. These problems are complex and hard to tackle at once, so we tried to first get the simple case right, which in the case of skin tone ranges, for example, was portraits with front-facing faces. We mastered the production scale, and then we expanded to harder cases and more applications. And overall accurate is not synonymous with fair. Biases need to be managed proactively. The system is not going to do that on its own. And we should not be afraid of sacrificing other metrics when trying to improve fairness. We learned about many issues when we looked closer, and we ended up improving performance for all groups and did not need to sacrifice, for instance, accuracy for fairness. Now, inclusive features such as skin tone ranges and hair pattern search make the user experience more inclusive by giving the users control over their experience. But we would also like for everyone to feel welcome and represented on Pinterest from the start of their journey. So to improve user representation, we launched skin tone diversification in various surfaces so that no one has to work harder to find content that's relevant to them. We've diversified search results for beauty and fashion queries, fashion product recommendations in shopping discovery surfaces, and we welcome new users with a diverse initial home feed when they first join Pinterest. Diversification approaches aim at re-ranking content to make the set of items that is surfaced more diverse by default. One common approach is to boost or discount scores for content that matches a diversity attribute or that is similar to other items above in the ranking. While boosters are simple to implement, they tend to become tech debt. They are tuned at the time that they are introduced, and then they are forgotten. More boosters get added, and they are not optimized together. So over the past couple years, our diversification approaches have evolved from greedy re-rankers to multi-objective optimization with DPP, determinantal point processes. So we first started with simple greedy re-rankers that take as input a list of pins ranked by their utility scores, the pins' skin tones, and score thresholds, and re-rank them to produce a diversified ranking. We deployed these simple approaches in various product surfaces, and they were effective at increasing diversity with neutral to positive impact on utility metrics. However, these simple approaches do not balance diversity and utility. They do not generalize easily to many different diversity dimensions, and multiple score thresholds are just not scalable. So we evolved diversification to a multi-objective optimization framework that can balance various utility functions and diversity using DPP, determinantal point processes. DPP is a machine-learnable probabilistic model used in physics for repulsion modeling and more recently in recommender systems. DPP is parameterized by a positive semi-definite kernel matrix whose diagonal entries represent the utility of each pin, and the utility score of a pin can be a function of different utilities. And the off-diagonal entries represent the similarity between pins based on different diversity features, such as, for instance, the skin tone in the pin. And per this model, the probability of a selected ordering of pins is proportional to the determinant of the kernel submatrix restricted to that subset. It increases with the utility of selected pins and decreases with the similarity of pins. And so maximizing the determinant of this kernel submatrix ends up promoting high utility and high diversity in the pin ordering. So I'd like to show you an example parameterization of DPP. We first define a utility matrix whose diagonal entries are function of utility scores. We also define a symmetric similarity matrix whose entries are similarities between pairs of items, and they could be computed, for instance, as a function of item embeddings. We have three parameters, such as theta, which balances the trade-off between utility and diversity, and some learnable functions, such as f and g, using deep neural networks. And using these, we define the kernel matrix, that is this Gramian matrix, as a product of the utility and similarity matrices. And with this parameterization, the probability of a subset Y of pins is a function of the determinants of the utility and similarity submatrices U and S restricted to the columns and rows in the subset. And the log of this determinant, as you can see, is a weighted sum between a utility term and a diversity term, where the theta parameter balances utility and diversity. And I show here more explicitly an example for a simple 2x2 matrix for the expression of the log-det determinant. Now, DPP is NP-hard. However, thanks to its submodular property, a DPP solution can be efficiently approximated using a greedy algorithm by greedily selecting the next item to add such that the incremental determinant is maximized. This side-by-side is an example for the query short hair in search, where on the left, we have the greedy re-ranker with thresholds, and on the right, we have the results with DPP. The score thresholds in the greedy re-ranker limited the diversification attempts. But on the contrary, DPP's flexibility allowed us to generate a set of results that had high diversity and high utility. Our experiments in various surfaces showed that DPP can achieve on-par diversity and utility compared with greedy re-rankers. But it balances diversity and utility in a way that allows to expand the coverage of diversification to more beauty and fashion queries, and to multiple diversity dimensions in a scalable manner. In our launches of diversification based on DPP in various production surfaces, we observed gains in diversity metrics with neutral to positive impact on utility metrics. And so this suggests that the systems may not be operating at the Pareto frontier between diversity and utility, as we can increase the diversity without negatively impacting utility, or sometimes even increase both. So if we think further ahead, we can also envision moving the diversity-utility Pareto frontier. For instance, we understand that diversity at the end of the funnel is limited by diversity earlier in the funnel. So working end-to-end throughout the pipelines can help improve the diversity-utility frontier. So I would like to conclude by sharing some recent feedback from pinners. Hearing from pinners and creators that our work is making a positive difference in their lives is the most encouraging reward for our team. And so I would like to leave you with a message of hope that change in technology is possible if one is intentional about it. I thank you very much and wish you a pleasant conference.